Okay, hello. Welcome to the next session of Dynamics PT, the first session of what is it called, computer recorded Dynamics PT session. Today I'm going to focus on two questions. I'm going to focus on tutorial 9, and the final two questions of tutorial 9 actually, which is something to do with conservation of linear momentum. So it's actually quite a bit of concept itself. So I want to take things out and just explain these two questions specifically because it ties very deeply. It has a very deep connection with tutorial 10, which is going to be the next tutorial we're going to discuss in these few days. So first of all, let's talk about the main important understanding in tutorial 9. So we're going to talk about something which is known as CR. Sorry, we're going to talk about C. So we're going to talk about COL, conservation of linear momentum. So what is actually the conservation of linear momentum? According to the conservation of linear momentum, if there are no external force, if there are no external force acting on a system, if there are no external force acting on a system, basically when I say system, I didn't say body, I say a system, what happens is that the summation of initial momentum is equal to the summation of final momentum. So let's recap. So what does the conservation of linear momentum say? Conservation of linear momentum is that if there are no external force, let's say if there are no external force acting on a system, I will define what is external force in a while. It says that if there's no external force acting on a system, the initial momentum of the system is equal to the final momentum of the system after a certain change. No matter what changes, as long as throughout the changes, there are no external force acting on the system, the initial momentum equals the final momentum after a certain change. So first of all, let's define what is external force. So to understand what's external force, we first need to know what is a system. So first of all, a system is basically, we can solve a collection of bodies, or basically something you draw a boundary on. Let's say today, let's say just for explanation, let's say today I have 1, 2, and 3 particles. Let's say I have 3 particles. And if today I were to define a system, so let's say there are 3 particles. So this particle exerts a force on this particle. And this particle will definitely, due to action-reaction pair, will also exert a force on this particle. Let's say this is what's happening. And also, subsequently, this particle will exert a force on this particle. And also, due to the action-reaction pair, this particle will also exert a force to this particle. And let's say, let me just give a different scenario. Let's say today, we have this particle also exert a force on this particle. And due to action-reaction pair, this particle exerts another force on this particle. Now, let me explain to you what does it mean by external force and a system and stuff like that. So if today, now take a look at this yellow color line. If today I were to draw my system boundary, I would just assume that this particle itself is a system. I would draw my system boundary here. It means that this force, this red color force, and this purple color force, which is acting on the particle inside here, is considered to be an external force. Okay, and repeat. Let's say this yellow color boundary here, this is a system. I assume that this particle is a system itself. When I say this particle itself, it means that this particle is my only system that I'm interested in. And since this purple color force are the forces which is acted by 2 particles which is outside the system, these 2 forces will be considered to be an external force. These 2 things will consider to be an external force for the system inside here. Now, you might wonder, how about this purple color one? Why don't we assume these to be external force? Because these 2 forces are forces which is caused by something which is from the system itself. So let me be very clear. Of course, within these 2 interactions, this particle experience force from this particle, and due to action-reaction pair, this particle also experience force from this particle. However, if today we are only concerned about a system, so this is the system that we are concerned about, only these yellow card, these circled forces are considered to be external force because they are caused by particle which is which is caused by a particle which is outside of the system. So it's very important to know about the understanding of, let's say, system boundary in this case. So these things are system boundary. So as I established, if I draw my system boundary here, I will assume that the force caused by this and this particle, which is this purple color and this red color force, as an external force, and these two forces is not considered as any force at all, because first of all, it's not caused by particles outside the system, it's caused by a particle in the system, so it's considered so-called as an internal force, or it's not something that we think to consider in the first place, okay, because it's not caused by a particle inside the system. Now, if today, let's say I go through the, if today, sorry, let me just undo this. So if today, assuming that I were to have a change in definition, if today I were to draw a boundary across this whole thing, I want to draw this whole thing as a boundary, and I assume that this whole thing is my system. If I assume that this whole thing is my system, all these forces here, now they all became internal forces. They all became internal forces. You see that? They all became internal forces. Oh, my bad. Let me redraw that. I'm not very familiar with the system yet. Yeah, so let's see if I draw my system, my boundary across this thing. All these particles, all these forces, this purple force, this red color force, this green color force, all of these forces are now considered to be internal forces. Internal forces. Internal forces means that the sources of the force, the origination of the force does not come from any particle outside the system boundary. So in this case, inside the system boundary, there are forces, but these forces considered internal force, they are not considered as external force because they are caused by particles from inside the system. Now, so now we have a very interesting part, yeah? Interesting, what is it called, phenomenon, right? Let's take a look. Now, let's say, sorry. Okay, so let's do a bit of comparison now. Let's do a bit of comparison. Okay, accidentally wrapped off that thing. Let me just redraw that. Now, see, what I'm trying to state here is that if today I were to draw my system boundary across this particle, okay, if I were to draw my system boundary across this particle, there are two external forces, right? There's one external force from this white purple force, and one external force from this red color force caused by this particle and this particle respectively. So if today I were to draw my system boundary across this particle, I can say with utmost confidence that in this particle perspective, linear momentum is not conserved, right? I can say that from this particle perspective, the linear momentum is not conserved because there is external force, and the condition for conservation of linear momentum is that there are no external force acting on the system. But in this case, if I were to draw my system boundary across this particle only, I would realize that there's actually external force. In fact, there are actually two external force, which is this purple color force and this red color force acting on this system. So it means that linear momentum is not conserved for this particle, let's say this particle B. It's not conserved for particle B. So this is not conserved for particle. Oh, sorry. This is A, so it's not conserved for particle A. Linear momentum is not conserved for particle A because there is external force. However, if today, let's take a step back. Let's say if today I were to not draw my system boundary here. Let's say for today, for this argument's sake, I were to draw my system boundary across this whole thing, right? Across this whole thing. This is my system boundary. And I take a step. Since there are no external force, assume that it's in a weightless environment, there's no gravity. In the external force, we see that there are actually no forces acting on this boundary. So if I were to draw this conservation, or if I were to draw this system boundary across this whole thing, I could, with utmost assurance, says that linear momentum of system is conserved. Do you see that? So here's the interesting part. Depends on where I draw my system boundary. I can actually have a bunch of linear momentum which conserve or not conserve. if I were to draw my system boundary across all the particles, and if I draw the system boundary across all the particles, all these forces now became internal force, and there are no longer any external force acting across this system boundary. When there are no other external force acting across this system boundary, it means that the linear momentum of this system is conserved. In other words, if I were to say that this is A, and this is B, and this is C, it means that the linear momentum of A, the initial linear momentum of A plus the initial linear momentum of B plus the initial linear momentum of C is equals to the final linear momentum of A plus the final linear momentum of B plus the final linear momentum of C. So let this F is final, is initial. So summation of initial linear momentum is equals to the summation of final linear momentum. However, interestingly, because if you were to draw the system curve around A, I could not say this is, if I were to draw the system curve around A, I realized that the momentum is actually not conserved if I were to draw the system curve around A only. So, in other words, I can say that the momentum of A initial is not equals to the linear momentum of A after final. Initial and final means after the forces have acted along certain periods of time or after a certain time period. Okay, so this want to make a point, like it depends whether does your momentum conserve, does the linear momentum conserve, highly depends on where do you draw the system boundary. And do you encapsulate all the particles or all the bodies that where the force originates from? If you can manage to encapsulate all the bodies where the force originates, it means that the linear momentum of the system is conserved because all the forces has now converted into internal force. Very interesting stuff. So, and let's go into something which is even more interesting. Let's assume this case. Okay, let's assume a very interesting case. Let's assume a projectile motion. So today we have a projectile motion. So let's say I have a gun barrel, and this gun barrel I shoot a cannonball into midair. It's very crude drawing. Please forgive my crude drawing. Now assume I have this gun barrel here, and now I have this particular cannonball. This is a cannonball. And this cannonball is now flying in midair. Apparently, it is flying in midair. So if I were to draw this cannonball as a particular system curve, so this is basically my system boundary. Well, this yellow color is a system boundary. And let's analyze the forces which is actually acting on this cannonball. So apparently, as most of you know, when the cannonball is actually in mid-air, the only forces acting on it is actually the gravitational force, right? There's only a gravitational force, so there's this weight mg force acting on it, so it's pulling it down. So as you can see, there's only one force acting on this which is cannonball, and basically it's the gravitational force. So there's actually only one force, and this force apparently, of course, is a external force because this force is caused by the Earth, and the Earth is actually not inside our system boundary, and this force actually crosses the boundary curve, the system boundary, and hence this is an external force. So obviously, for this cannonball, the linear momentum is not conserved. However, let's take a step back. Is it that simple? Is it really that the linear momentum is not conserved? Now look at that. Vertically, there is an external force, which is weight. But horizontally, there is actually no external force. Interesting, right? Horizontally, there's no external force. Vertically, there's external force. And apparently, because, what is it called? Because this is actually a mid-air situation, this cannonball itself, of course, have velocity, right? It has velocity in the horizontal direction. So we have on VH, and we have velocity in the vertical direction. VU. Let's say vertical VV. Okay, so let's say VH is the final horizontal velocity and UH is the initial horizontal velocity. So in other words, let's say I shoot this cannonball, and after a certain amount of time, I actually press my stopwatch, and so after I shoot this into the air, I immediately measure the horizontal velocity of the cannonball, and I do that at UH, and I start my stopwatch. Maybe after 5 seconds, I recorded the horizontal velocity of this cannonball, and I did it as VH. So I do the same thing for the vertical velocity. So when I immediately after I launch the, what is it called, the cannonball, and I denote the initial vertical velocity, which apparently is upwards, is the initial vertical velocity. And after like 5 seconds, I recorded the vertical velocity of the, what is it called, uh, cannonball. And I realized, and I denoted that as the final vertical velocity. So let me just make it clear again. UH is the initial horizontal velocity. VH is the final horizontal, sorry, let me repeat, sorry. UH is the initial horizontal velocity. VH is the final horizontal velocity. UV is the initial vertical velocity. And VV is the final vertical velocity. Initial horizontal velocity, final horizontal velocity, initial vertical velocity, final vertical velocity. And apparently, now, this is the interesting part. From this thing, we can actually make some very interesting distinction. We can actually say vertically, because there's an external force, vertically, there's an external force. So the initial vertical momentum is not equal to the final vertical momentum, right? That makes perfect sense. Initially, it's moving upwards. Finally, it's moving downwards. This is a vector quantity. This will be positive. This will be negative, or the direction will be opposite. So apparently, it's correct. We have proof that vertically, the momentum is not conserved. However, if we take a look, the initial horizontal velocity, which is the initial horizontal momentum, which is MUH, is actually equals to the final vertical horizontal momentum, right? Let's take a look. As we know, for a projectile motion, the horizontal velocity doesn't change. In other words, we can say with great, what is it called, certainty, that UH is equals to VH. UH is equals to VH. The horizontal velocity initial and after the recording period is always the same. So look at this situation. Let me just repeat one. I know I'm doing it a bit fuzzy, but let me just repeat so you understand what I'm trying to say. Look at this situation here. We only have one external force, and the force is actually this gray color part. There's only one external force, which is gray. And this force is actually acting in one particular direction. If your external force is acting in only one direction, momentum is not conserved in that direction. However, momentum is conserved horizontal to the direction. So you see, the external force is vertical, so the vertical momentum is not conserved. However, since external force is only on the vertical direction, horizontally, there are no external force. So horizontally, momentum is conserved. So in this case, we realize that vertically, momentum not conserved. Now, but horizontally, momentum is conserved, right? Is conserved. See that? It's a very interesting part. Vertically, momentum is not conserved. Why? Why is it that vertically momentum is not conserved, but horizontally momentum is conserved? Because vertically, sorry, because vertically, there is external force. In other words, the weight. However, horizontally, there's no external force. So this is very important stuff. Please keep in mind. Look at that. Vertically, there's external force. Horizontally, there's no external force. So horizontally, momentum is conserved. Vertically, momentum is not conserved, right? So this is something that's very important that I would like more of you to understand. So first of all, we're talking about this conservation of momentum. So don't worry, I will actually share this note and understanding on the group so that you can just take it if you want. Now, so we've done with that. So we're cool with that. Now let's talk about, let's put this into practice. So when you put it into practice, maybe you understand what's going on in the matter. So let's take a look at this thing. Okay, let's take a look at this thing. Now let's take a look at tutorial 9, question 3. So block B has a mass of 50 kg. So block B has a mass of 50 kg. So this block B has a mass of 50 kg, and it rests on the surface and the cart having the mass of 75 kg. Now, and a spring which is attached to the cart but not the block is attached to the cart, not the block, is compressed to 0.2 meter, and is compressed 0.2 meter. So this is basically our E. This is basically our E extension of the spring itself, E, and the system is released from rest. We need to determine the velocity of the block after the string becomes undeformed and the velocity of the block relative to the cart. So in other words, we need to find the velocity of the block in the cart. So let's denote the cart as C. Let's denote the cart as C, okay? This cart is C. Let's denote the cart as C. Now, so how do you do this question? So apparently, this is quite an interesting question. Now look at that. Let's dissect this question bit by bit. There is a spring. This spring was initially compressed. Now they want to find out what will be the velocity of the cart and the block after it's uncompressed. Now please take note about this. When we talk about spring, right? Spring actually has a non-constant force when it expands, right? Remember what's the formula for spring force? The formula for spring force F is equals to Kx. In other words, sorry, it's not Kx, Ke, where E is the extension of spring. And think about it, when the spring is constantly undeforming, the extension actually changes. It means the forces change with time. So it's kind of hard, but it's kind of unwise to actually put this in the force equation, because if you were to put in the force equation F equals to ma, F is not constant. So we will try to what is it called, refrain from doing question like this using the force method. Instead, we'll try to opt for other methods. In this case, I will opt for the energy method, definitely, because it encapsulates the initial and final velocity. And I also opt for the conservation momentum method, because let's set up the energy equation, you will know why. So first of all, let's set up the energy equation. So for the energy equation, we know that for a system, the change in kinetic energy, that's what I explained before, plus the change in gravitational potential energy, plus the change in elastic potential energy is equals to the summation of external work done on the system, right? External work done is basically work done by external forces, and the understanding of external forces is exactly what I just explained before. So in this case, let's look at this. If you were to solve this equation, I need to first set my boundary. And apparently, I wouldn't want to set my boundary here, right? If I want to set a boundary here, I do not include this spring. And I do not, and this, the force of the spring acting on the cart, the force of the spring acting on the block is considered as an external force if I were to put my boundary across this B itself. If the force spring is an external force, it means that this work done will also be changing, because my force of the spring acting on B will be changing constantly. So I don't want to deal with this kind of thing. It's very messy. So what I will do is that I will intend to draw a boundary across the cart and the block, across everything. If I were to draw across everything, you can see there's actually no external force acting on this thing, right? Then you might say there's a weight, but the weight is cancelled by the normal force. So there is no net external force. Yeah, there's no net external force acting on this thing. When there's no net external force acting on this thing, I can say that the external force work done, the work done by external force is zero. The gravitational potential energy is zero. Now we only have two terms. We have the kinetic energy and the changing elastic potential energy. So what is the change in kinetic energy? So the change in kinetic energy is equal to half the final kinetic energy of the system minus the initial kinetic energy of the system. The final kinetic energy of the system is equal to half mc, which is the mass of the cart times the velocity of the cart squared, plus half mv, mass of the block, plus velocity of the block squared. Okay, one by one. So this is the final velocity, final kinetic energy of the system. This is a final kinetic energy system minus the initial kinetic energy of the system minus the initial kinetic energy of the system, which is zero. So this is my change in KE, plus change in GP is zero, plus now change in EP. What is the change in elastic potential energy? In this case, only the string can store elastic potential energy, so it will be final elastic potential energy minus initial elastic potential energy. So it says after the spring becomes undeformed, so the final elastic potential energy apparently is zero, and the initial elastic potential energy will be the half K E squared, which is initial, what is it called, compression of the string, which is actually 0.2 meter, is equals to 0. If you were to arrange this equation, you will have something like half mcvc squared plus m squared is equals to half squared. That's the whole thing. That's the whole thing we have. Very simple. So now think about it. Look at this. How many unknowns do we have? We actually have one unknown, which is the magnitude, the VC, and one unknown, which is VB. Now, please think, what is VC and VB? VC and VB are just basically the speed of block C and block B respectively. It's not velocity, it's just a speed, because this is basically scalar quantity. This is speeds. Okay, this is not the velocity. There's no direction involved. I just made that clear. But eventually, there's actually two unknowns here. When there's two unknowns, it means that this is basically just the first equation we need. So we need another equation which also involves VC and VB. If we have another equation to involve VC and VB, we can basically solve this equation. And if you want to talk about another equation, another kinetic concept involved the velocity of particles in body, apparently we're going for the linear momentum equation. In this case, if my system boundary is drawn across the whole thing, and across this whole thing, there's no external force, because although there's weight is counteracted by the normal force, we can definitely say that momentum is conserved. It's conserved horizontally, it's conserved linearly, it's conserved in every single direction, because there is no net external force. There is no net external force. Let me repeat. So if there is no net external force acting on this thing, it means that we can safely apply the conservation of linear momentum. So how do we apply that? Let's go on to the next part. So to apply conservation of linear momentum, you need to know that according to the formula, mb, define the initial linear momentum, which is mb, and this is actually a velocity, initial velocity of the block times the mass of the block plus initial velocity of the cut plus the mass of the cut is equals to mass of the block plus final velocity of the block plus mass of the cut plus final velocity of the cut. This one you must understand. Now, after you establish this, we know that the initial velocity is on 0, because it can be 0. And now, initial velocity is 0, right? Because it is released from rest. Now what is VB? Now, we need to establish some boundary for VB first, right? We need to establish some boundary for VB first. So VB is actually equals to the velocity of B, the magnitude of, it's actually the velocity of B, which is equals to the speed of B, but this is basically VB in terms of the magnitude. In other words, the speed is basically the magnitude of the velocity component. So VB can be placed as VB. Now, assuming that when this one release, V will move to the right, so just assume that VB direction is 0. Don't be so worried about placing the numbers, because it will eventually arrange itself. And VC is the velocity of the car, which we can also put it in simplified form of VC and 100 because we assume that when we release this thing, B goes to one side, C goes to the other side. Now, here's an interesting part. VC here has a direction of 180 degrees and has a magnitude of speed VC. So this VC is equals to the VC here. This VB equals to the VB here. The speed is equals to the magnitude of the velocity. Simple as that. So after we know this, we can straight away place this inside here. We can use this understanding, place this inside here. We can have MB. Now VB is equals to VB direction 0 degrees plus MC VC direction 180 degrees. Now, as I said before, we can basically do what? We can just cosine the whole thing, resolve everything in the J direction. We can just resolve everything in the I direction by cosine everything. If we cosine everything, we get something like this. MB VB minus MCB. So this is when you cosine everything, resolve everything to J direction. Resolve to J direction. That's what you do. When you resolve to J direction, you will get this thing here. When you achieve this thing here, eventually you have one more equation. So this will be your second equation. So for the first equation and the second equation, apparently you can find your VB velocity, your V velocity of C. And if you want to find the velocity of block relative to the car, you are trying to find velocity of the block with respect to the car. Just do the simple, what is it called, relative velocity equation. put this together and you can basically get the answer you want. So this is basically the steps, the layout to solve the equation here. I'll upload this thing onto the group, and generally speaking, if you saw this, you can try to get along the way. If you have any question, please WhatsApp me. I will reply you as soon as possible. All right. Now, this is done with tutorial 9 question 3. Now let's talk about tutorial 9 question 4. This is a very interesting question, right? This question is actually more than it meets the eye. So I'm going to spend quite some number of time to actually dissect this equation, and I hope that you can actually understand what I'm trying to say here. Now, let's take a look at this equation, this question here. And this question says that we have particle P of mass 4 kg is placed on the smooth inclined surface of a triangular block B of mass 20 kg. So this triangular block B, this thing here is 20 kg. And we have this, and the system we use for rest determine the velocity of P and the velocity of P when P reach the bottom. You get the size of particle B, P, blah, blah, blah. Here's the interesting part. Think about it. Most cases, when you deal with a particle in the wedge will not be moving. The wedge is basically fixed onto the floor. When the wedge is fixed onto the floor, this becomes an extremely simple question because what you have to do is just, first of all, find out the forces acting on P and do the energy. So you want to find the velocity of P when P reaches the bottom. If today B is fixed on the ground, you can just use a simple energy equation to find what's the velocity of P when it reaches the bottom. But today, things change because B is not fixed on the ground. B is not fixed on the ground. When B is not fixed onto the ground, it means that when P moves down, B will actually move to the left, right? When P moves down, B will move to the right, left. So when we have situations like this happening, then it's actually quite tough for us to do it, but it's okay. Let us dissect bit by bit on how do we solve this question. Now let's look at the question. If the system is released from rest, determine the velocity of P and B when P reaches the bottom. Now, so first of all, we want to talk about when P reaches the bottom. In my personal understanding, the first thing that I always want to do when I look at a question like that and looking from the final equations, I will always want to solve this using the energy equation. So first thing I apply, first concept I apply is always conservation of energy. So in this case, I'm not going to waste my time. So when I do conservation of energy, I'm definitely going to apply the, what is it called? I'm going to apply conservation energy across the whole thing, right? Across this whole thing. So yeah, I'm going to apply conservation of energy across this will be my system boundary. So just repeat, this will be my system boundary. Why do I want to choose my system boundary? Why would I choose this thing as my system boundary? The reason is because if I choose this thing as my system boundary, there's a normal force which is acting here along, which is acting on P. And these forces change in certain ways. And if these forces change in direction, which I will explain when the normal force acting on P, and this force might not be constant and it might change. I'll explain to that later. But in other words, if I were to draw a boundary across P, I wouldn't have any information on P. So with all due respect, I will just not draw a system curve around P. I will draw a system curve around P and B. If I want to draw a system curve around P and B, I can apply conservation of energy. And let's take a look. What is the forces acting across this whole thing? Now, what are the forces acting across this whole thing? So, first of all, we have, if we take a look at the external force acting across this whole system, apparently, we will have the, what's it called? We have the weight, right? We have the weight, which is mvg, is external force, and this mpg, you see, external force is a weight acting by Earth on B and P. Now, how about the normal force acting on P? Now, the normal force acting on P is caused by B itself. The normal force acting on P is caused by B itself. So it's an internal force because our system curve is drawn around the whole thing. So the normal force of P acting on B and on B of B acting on P is an internal force, so it's not considered in the calculation. Is there any more external force? Now we have two external forces we just established here. So please take note, both these external force, it's important to know that both these external force is acting perpendicularly downwards. Both these external force is acting perpendicularly downwards. So please take note, I only denote external force. I do not denote internal. I did not note the internal force. There's actually one more external force acting on this thing, actually. So the external force is actually the normal force of this table acting on this system, right? This table is not part of the system curve. This table is not part of the system curve, we repeat. So in that case, the normal force acting by the table on this chunk here is actually known as an external force. So there is an external normal force here, which I denote as N. Okay, interesting. Let's look at that. There's actually three external force acting on it, and there's actually no friction. There is no friction, right? Let me see. Yeah, neglect friction in all surfaces. When there's no friction, it means that all the external force acting on this surface is vertical. All the external force acting on this surface is vertical. But doesn't matter. In this case, we just need to apply conservation of energy, and let's see how do we solve this equation. Now, if I were to apply conservation of energy, I need to use the equation, right? Change summation, change in KE of a system plus change in gravitational potential energy. Now, change EP I didn't write because it's actually there's no elastic form here. It's equals to the summation of work done by external force. Now, first of all, you might ask, is there any work done by external force? Now, please take note, as I explained before, the work done by external force, we only include friction and all other external forces. We do not include elastic forces. We do not include gravitational force. So in this case, the work done by external force is 0. Then you might ask, how about this normal force? This normal force is an external force and it's not gravitational force. Well, the answer is that the work done by this external force is also 0 because there is no distance moved in the direction of the force along the contact point of the force. In this case, this is the normal force, right? It is the contact point of the normal force, but this block doesn't actually move upwards. If this block doesn't move upwards, it means that there's no distance traveled in the direction of the force. So in this case, the work done by this normal force is also 0. So essentially, bottom line is the work done by external force is 0 in this case, okay? Because first of all, we don't include gravitational force. Second of all, the work done, the distance traveled in the direction of this, the distance traveled in the direction of this force is 0, okay? So we establish it is 0 here. Now, the change in kinetic energy is actually equals to the final kinetic energy of the system minus the initial kinetic energy of the system. So basically, we can say this is equals to half ma va square final kinetic energy of P, this P, sorry. The ball is known as P because they like to put it as P, so it's P. And half mp vp square plus half mb vb square. This is the final kinetic energy of the particle and the block minus the initial kinetic energy of the particle and the block, which is essentially 0. That's the change in kinetic energy. Final kinetic energy of the system minus initial kinetic energy of the system plus final gravitational potential energy of the system minus initial kinetic energy potential of the system. Initial gravitational potential energy of the system. So the final gravitational potential energy is 0 because at the end of the time, the particle P actually shifts to the ground. There's no final gravitational potential energy if we assume that this is our 0 neutral line. However, the initial gravitational potential energy is only possessed by P because B is always on the ground. So it just equals to mp g and the height. Let's just say this 2m is equals to height. This is height. Height is equal to mp g h. So for this equation, let's do a bit of arrangement and what's it called trimming. We can essentially say that. So you can say that if you throw the half, you put this here, you throw the half the other side, you can say that mp vp square plus mb v square is equals to mpgh. This is what is going on. Sorry, there's a 2 here. I forget the 2. There's a 2 here. So now after we have solved this equation, this is done. This is not perfect. So this is basically our first equation of the day, solved by conservation of what is called energy. But however, here's an interesting part. Although this is solved by conservation of energy, let's take a look at how many unknowns do we have. We actually have one unknown. So I shouldn't use this. Yeah, I should use something. We have actually one unknown. We have one unknown and 2 unknown. which is the velocity of the speed of P and speed of B. Now, please note Vp is the speed of P and Vb is the speed of B. They are not velocity, they are speed because it's a scalar equation, as I've mentioned many times. So, this equation is formed by conservation of energy. So, is there any other equation we can use? Now, the other equation we can actually use is actually the conservation of momentum, right? Now, you can use the conservation of momentum equation. However, please take note. Momentum, since there's only vertical external forces, So the first question we ask ourselves is that, since there's only vertical external force, it is very clear that horizontal momentum must be conserved. Now the next question is vertical momentum conserved? Because there is vertical external force, yes, but maybe, just maybe, the normal force will cancel out the, weight. If the normal force cancels out the weight, it means that there's no net vertical force, it means horizontal and vertical momentum are all conserved. But the answer is that that's not true. How do we understand, how do we even guess that these forces wouldn't cancel each other? Well, that's a very simple and neat trick actually. First of all, we need to take a look at Newton's second law, where it says that F is equals to ma, or more accurately, summation of force is equals to mass times acceleration in the vertical direction. So in this case, F equals to ma actually works in this system too, but it's actually mass of P plus acceleration of P plus mass of B times acceleration of B. So if you want to know, is there any net vertical forces? It means that there must be a vertical component in either P or B. Let me repeat. So if you want to apply Newton's second law on this system to see if there is a net vertical forces, what we can do is that we can observe the acceleration. If in this system, one of this body has an acceleration component in the vertical direction, it means that there is a net force in the vertical direction. Let me repeat. If in this system there is an acceleration in the vertical direction, it means if there's a net acceleration in the vertical direction, it means that there must be a net external force in the vertical direction. Take a look at it. The acceleration of B is horizontal, so there is definitely no vertical component for the acceleration of B. How about for the acceleration of P? Now P is sliding downwards. If P is sliding downwards, although it's not actually a direct motion like it's a haphazard motion, it definitely has an acceleration in the vertical direction. If you were to resolve this equation horizontally and vertically, vertically, MPAP vertical wouldn't be a zero number. If this is the non-zero number, it means that F vertical, summation of F vertical is also non-zero. In other words, I just proved that the vertical forces could not be, the net vertical forces could not be zero. Now, if you don't understand what I'm trying to say here, please review this equation. But I'm gonna just summarize this one more time. First of all, we know that the external vertical force would not cancel each other, because if we were to apply Newton's second law across this boundary, we realize that there will be no vertical acceleration for the B chart card, and there will be vertical acceleration from the P particle. If there is vertical acceleration from the P particle, it means that the net vertical forces must be non-zero. If you don't understand this concept, please come and find. Okay, but anyway, we just proved a very interesting stuff. That that the vertical forces wouldn't cancel each other. Let me just repeat that. Okay, summation of force in this system must be equals to MP plus AP plus MB plus AB. Now, if we resolve vertically, the summation of the vertical forces external vertical forces must be equals to mass of the particle times the vertical acceleration of the particle plus 0. This is 0 because cut B doesn't have the vertical acceleration. So if you look at this equation, of course this is non-zero because P is sliding downwards. it means that this must be non-zero too. So it means the external vertical force is non-zero. I should explain this way. I'm so sorry that I wasted so much of your time just talking about all these things. Please forgive me. A bit of a tight schedule here. Okay, now, yes. So since we know that the external vertical force would be non-zero, since we know that the external vertical force would be non-zero, it means that momentum is only conserved horizontally. Momentum is not conserved vertically. So we can say with utmost confidence that vertical momentum is not conserved. Horizontal momentum conserved. Yeah, we're happy because we can use this horizontal momentum understanding to solve the equation. So to solve for the horizontal momentum equation, here's what I'm going to do first. So how do I establish this horizontal momentum equation? So the horizontal momentum says that let's just say conservation of horizontal linear momentum equation is equals to the mass of the particle plus the horizontal so initial final minus initial, right? So the mass of the particle times the initial, let's just say the initial horizontal momentum of P plus mass of the block plus the initial horizontal velocity of V times the initial horizontal velocity of V is equals to the mass of the particle times the final horizontal momentum of P plus mass of the block times the final horizontal momentum of V. Now we have this equation here. Now here's the very interesting part. What is this thing? We know that the initial part is definitely zero because released from rest, so this is zero. Is equals to mass of the particle times the final velocity of the particle, h, in the horizontal component, plus mass of the block times the final velocity of the block in the horizontal direction. Now, we want to solve this thing. These two things are the main problem here. So, first of all, let's take a look. What is Vp? Vp is the velocity of P. Now, this is the misconception that most important. So what is so let's first of all let's know what Vp is first. Let's just focus on how do we find velocity of P in the horizontal direction. Now, velocity of the P in the horizontal direction is just basically your velocity of P resolved in x direction, right? Velocity of P resolved in x direction is equals to Vp dot product with 0 degrees, right? Vp dot product with 0 degrees. At this moment, most of you should know how to do dot product, okay? But the main problem is how to find Vp in the first place. We'll do that later. So to find Vph is the velocity of B in the horizontal direction. It just equals to the velocity of B, the velocity of B dot product with the 0 degrees direction. Now let me just repeat again. Vph is the velocity of the particle P in the horizontal direction, which is equal to the velocity of P dot product with 0 degrees, because it is resolving to the x direction. Vph is just basically velocity of P resolved to the x direction. Vbh is actually the velocity of B, the horizontal velocity of B, which is equal to the velocity of B resolved to the horizontal direction. In other words, dot product with 0 degrees. Let's do it for this, much easier. So Vb, we can basically just know that we know that Vb is going horizontally. We know Vb is going horizontally, and this Vb can be represented as a magnitude with a direction of 180 degrees, because assume the Vb is moving back and Vb is going down. So just do this. Okay, dot product with 0 degrees. Now, if you were to do a dot product, means what? Dot product means that you cos the difference in angle, which is equal to negative Vb. Now, please note this Vb is the speed of velocity of B, the speed of block B, which is actually equals to this Vb here. So this Vb and this Vb is the same. Okay. Then what I eventually do is I find the the component, the velocity of v in the horizontal direction, which is just the velocity of v dot product with 0 degrees, you get negative vb, where vb is the magnitude of the velocity. Now, please take note to use this method. This method will make sure the equation is correct. If you were to just say, oh, vb here is just equals to vb, you'll be wrong because they will disobey the equation that you do here. But remember, when we resolve the velocity in the horizontal direction, we need to dot product with 0 degrees. That's the actual way to do it. Now this is done. Now, how about VP? Now VP is a bit crazy. Right? VP is something we can solve because what is VP? Now most people will say the VP is the velocity of P is equals to VP direction, and they say this is 30 degrees, so the direction of VP should be negative 30. Most people will do this. But actually this is wrong. This is actually wrong because VP is only in negative 30 degrees if the block is not moving. Now, the velocity of P is not negative 30 degrees. If the block is not moving, yes, velocity of P is negative 30 degrees. But if the block is moving this way, P might be actually going in some other direction, maybe in this position. So it just curve downwards in a motion like this. Can you imagine that? If you cannot imagine that, what you can do is that you can try to simulate this experiment by actually trying to put your, by using a ruler and placing your pen on top here. You try to move the ruler and you try to slide this pen along the ruler. You realize the resulting curve that you form will be something like this. It wouldn't be a straight line. If it's not a straight line, it means that velocity of P is not negative 30 degrees. I repeat, velocity of P is not negative 30 degrees. So if velocity of P is not negative 30 degrees, it means that we cannot dissect velocity of P this way. We will just give it a random angle theta, where theta just equals to velocity of P. Dot product with 0 degrees, and this thing becomes Vp cos theta, right? Because theta minus 0 is theta. This cos of whole thing, that's your VPH. So now let's sub this inside here. Let's put this inside here, put this inside here, and place this inside here. And eventually, we have our linear equation. We have 0 is equals to NP VPH. So if you were to compile the thing, it goes NP VP cos theta, and this plus NB negative V. So this is our second equation. So what is our first equation? This is actually our first equation, right? This is our first equation. So which is, yeah, this is actually our first equation. Just copy this thing and put it down there so it's easier for you to see. This is actually paste. Right. And I love one word. Right. Now look at this. So it's our first equation, it's our second equation. Now let's take a look. What are the unknowns do we have? How many unknowns do we have? We have, so in this case here, we have actually the speed of P as unknown. We have the speed of the block, VB is unknown. This is speed, and this is not velocity because we assume no direction. We have the direction of velocity of P, which is unknown, which is theta here. And means that we have three unknowns. We have actually three unknowns. Three unknowns with two scalar equations. Three unknowns with two scalar equations. We can't solve this thing. So we need one more equation. We need one more equation to relate VP and theta. Now, the good thing for us is that we actually have exhausted the kinetic analysis of this question. But what we haven't done is that we have not used a kinematic analysis. So what we are going to do now is that we are going to use the kinematic analysis. So kinematic analysis. So what is the kinematic analysis that we have here? So to do the kinematic analysis, let's take a look here. So to do the kinematic analysis, let's just copy this whole thing. See if we can make it work. Let's copy. Just oops. Oh, okay. Sorry, I can't copy and paste a diagram. Never mind. Let's just do this. Just copy and paste on the kinematic analysis. This whole thing here. So can I crop this thing? Yeah. I don't think don't think I can crop this thing, but never mind. So how do we do kinematic analysis? Let's just use this thing as a whole. So to crop this thing, or maybe I can use this. Oh no, I can't crop this thing. Anyway. So to do the kinematic analysis, what I'm going to do now is that I'm actually going to split the direction. Look at P. So we know that P is not going directly downwards, right? P is not going directly downwards. The velocity of P is upwards. So velocity of P is equals to velocity of P with respect to B plus velocity of B. Okay, so this is basically a relationship between the particle and the body. So since we do not know the velocity of P, and you look at this part here, velocity of P is direction theta, P is theta, it means that we can just sub this equation here and put it as Vp direction theta is equal to now. What is velocity of P with respect to B? Now this is very interesting because velocity of P with respect to B, in B perspective, P is definitely going in the negative 30 direction. Let me repeat. In B perspective, P is definitely going in the negative 30 direction. So we can say that it is Vp slash B direction, negative 2 degrees. Perfect. Plus Vb. Now what is Vb? Vb is something we can get from here, which is just Vb direction 180. Vb direction 180 degrees. So you must take a note that all the terms that I use is very consistent. I always try to relate this equation with terms that I have used above here. See that the terms that I have used above here, in this case I use Vb direction 180 as a Vb, as a velocity of B, I put it inside here because I need to use the same term. After I establish this is actually another equation. This is actually my third equation. Let me just put the notation. So this is my this is my kinetic analysis. So let's take a look at all the equation I have. So this is my first. So this is actually my first equation from this is my first equation from the energy analysis. This is my second equation from the second equation from the so this is my second equation from what's called momentum equation analysis, which is conservation of horizontal momentum, and this is literally my this is my third equation from my kinematic analysis. So basically, I have three equations. So conservation of energy, from conservation of horizontal momentum, and from the kinematic analysis. Okay, now let's take a look at how many unknowns do I have. The unknowns that I have now is actually Vp, the speed of P, magnitude of velocity of P, theta, direction of velocity of P, Vb, magnitude of the what is it called, velocity of B, and we have which that is introduce a new equation here. So it's velocity of P with respect to B, the magnitude of velocity of P with respect to B. So I have four unknowns now. If you have four unknowns, let's take a look how many scalar equations you have. You have two scalar equations and one vector equation. Now, a vector equation is equal to two scalar equations. So in this case, I have actually four scalar equations here. When I have four scalar equations here, it means that I can solve this equation. So let me repeat, I can actually solve this equation. So the question is, how would you want to proceed to solve this equation? Now that requires quite a bit of understanding. Excuse me. So to solve this equation, first of all, I will split this thing. I will split this term into two components. I will split this term into j component and I component. So I have Vp cos theta is equals to Vp slash B Vp slash B direction, so cos negative 30 degrees minus Vb. So that's the horizontal equation I have. Now, from this equation, it's very interesting. From this equation, I can actually substitute this part, and I can represent Vb in terms of Vp slash B. Once I resolve this to the horizontal I direction,